Hi everyone, welcome back. This is going to be the last section for multivariable calculus, and this section is known as a divergence theorem. When we're going to start by working with that theorem, and that theorem says let E be a simple solid region in and S is the boundary surface of E with positive orientation. So if you see this picture here that I have for you all, I have this region E. In other words, region E is this volume that is being bounded, and it's being bounded by this surface. Alright, this surface is made up of three different surfaces. The bottom of it, which is S1, the top part, which is S2, and then the figure all the way around, or the surface all the way around, which is surface 3. So those surfaces are bounding this region E, and they're going to have positive, those surfaces are going to have positive orientation, meaning that the normal vectors are going to be pointed outward from that region E that is being bounded. So let F be a vector field whose components have continuous first order partial derivatives. Alright, so we must have continuous first order partial derivatives in order to work with this vector field. Nice. Then what we're going to get is that the surface integral that we're observing here for that vector field is going to be equal to the triple integral over the region E, and that's going to be integrating for the divergence of that vector field with respect to that volume that the region E is being encompassed by. Now, what does this tell us then? Well, this actually tells us here in green that the outward flux of a vector field across a closed surface is the triple integral of the divergence of the vector field over the enclosed surface in R space 3. Now, I want you to kind of think about that just a little bit more. Now, this kind of goes back into what Stokes' theorem was saying. Stokes' theorem was just a surface that was bounding some sort of region, but we never really defined that region that it was bounding. All we were looking at was this surface being placed into this vector field. Well, now we want to take it a step further, and we want to take that surface. Now that surface is going to be bounding a certain region, and we're going to take that region and those surfaces and we're going to put them into a vector field. And we want to now analyze what is that outward flux of this vector field as we put this surface into that vector field. So in order to kind of illustrate this, I want to go over to Geogebra and give you kind of an example of what we want to observe. So here we are on Geogebra, the class that I set up, this multivariable class. And if you scroll all the way down, you have this divergence example. Now this divergence example is going to be the example that I'm going to do in just a little bit. Alright, but I want to illustrate what it is that we're doing here. So what I want to do first is I want to show the surfaces that we are going to be working with. And those surfaces are going to be here. And again, on the example in class, we'll look at those surfaces shortly. Alright, here we are. Those are the surfaces. We have a cylinder, we have an elliptic paraboloid, and we also have a plane here. The intersection of all of these surfaces, they're going to make a region that is being bounded. Now I'm going to eliminate the surfaces here, that way we can see that region. This is that region that we're going to be observing. It kind of looks like a miniature bullet. Alright, and this is what we want to observe. This is going to be the region that we're going to be placing inside of a vector field. So now we want to look at the vector field as we start placing this object in this vector field, and we want to see what is the flux that we're going to be observing for this vector field as it's moving across the surface for this object that is being placed into it. Alright, so this is what we're doing in this particular section. We're working with that divergence. Alright, so now that you get more of an illustration of what we want to see and what we're observing here, let's go back and let's go ahead and start with our calculations on an example. Alright, so now we're back. let's go ahead and let's work on this example. This example is going to say use the divergence theorem to evaluate this surface integral where the vector field is given by the components xy in the I component minus y squared divided by 2 in the j component plus z in the k component. And the surface consists of the three surfaces. And these three surfaces are the ones that we just saw in the previous example on GeoGebra, where we have this elliptic paraboloid, this 4 minus 3x squared minus 3y squared, and z is only going to be bounded between 1 and 4 for this surface. X squared plus y squared is equal to 1. So again, we have the cylinder, where this cylinder is only going to exist between the values of z is equal to 0 and 1. And then we're going to have z is equal to 0. So really quickly, what I want to do is I want to draw a depiction of what it is that we are looking at. That way we can extract what are the different surfaces and how are we going to work with them. Alright, so here's my depiction of what it is that we're looking at. Again, we have this elliptic paraboloid, and I'm going to denote the elliptic paraboloid in green here. The elliptic paraboloid is bounded between z is equal to 4 and z is equal to 1. And then we're going to have this cylinder, and this cylinder is going to be bounded between z is equal to 0 and z is equal to 1. And then we're also going to have z is equal to 0, which is the x and y plane. That one is going to be denoted by the orange piece here. Alright, so we have these three different surfaces that we're looking at. So the green one is 4 minus 3x squared minus 3y squared. The pink one here is going to be x squared plus y squared is equal to 1. And the last one is going to be that z is equal to 0. And again, they're all going to have their appropriate bounds. Now, when we want to figure out what is this surface integral for this vector field with respect to its surface, what we're going to have to do is we're going to have to use the divergence theorem, which means the divergence theorem is going to tell us, hey, you don't need to worry about parametrizing these surfaces or working with the surfaces. All you need to do is figure out what is the total region that is being submerged and integrate the divergence of the vector field with respect to that region. So for us, all we then have to do is we then have to interpret what is this region that is being submerged, or that what is this region that's being placed into this vector field. Alright, so that region E, we're then going to have to then evaluate. And this is where we need those triple integrals back from chapter 15. This is why we went through the whole process of figuring out how to do this within the rectangular coordinate system, meaning x, y's, and z's, triple integrals, or triple integrals in spherical coordinates, or triple integrals in cylindrical coordinates. Alright, now typically looking at this picture here, looking at this object, that region E, I don't want to use Cartesian. It might be a little bit difficult to use Cartesian here. I don't want to use spherical because I don't have a sphere, and I do kind of want to use cylindrical coordinates because it kind of looks like I can do this using cylinders, or in a two-dimensional aspect in R-Space 2 using polar coordinates. I believe that will make this easier. Alright, so that's one of the items that I observe first. Next, I want to find the divergence. Now, if you remember the divergence of the vector field, we discussed this in one of the previous sections. If you don't remember how we talked about divergence, I'm going to put a card on the top right hand corner of the video, and you'll be able to click on it and it'll take you back to that curl and divergence section. That way you can see how we work with the divergence of a vector field. So my divergence, as I'm working with this triple integral over E, the divergence of this vector field should be just 1. Alright, just like this. And I'm going to integrate that divergence with respect to the volume over that region. So what I then have to do is figure out how I want to triple integrate, or how do I want to set up a triple integral for that region. Now, what I'm going to say here is, at this point in time, I want to use cylindrical coordinates. So I want to use cylindrical coordinates for that region E. Alright, that means I'm going to need 3 items. I'm going to need my integrand, which is 1, and then my differential dv. Remember, when we change our differentials over to cylindrical, spherical, anything like that, we need that Jacobian. The Jacobian in our case, because we're switching over to cylindrical coordinates, will be r dz dr d theta. So let's now figure out what are these bounds talking about. Alright, so the easiest one, again, I always say it's the easiest one because I like the angle measurements for theta. So theta is actually moving all the way around. It's creating these circles all the way around this figure, no matter where we're talking about. So theta is always going to be bounded, in this particular case, from 0 to 2 pi. Alright, not too bad. The radius. The radius of this figure doesn't matter where it's at. Check out the radius. We'll do the radius in red here. The radius from here to here, or from here to here, or from here to here. Notice once the radius gets to that cylinder, the radius stays constant. But before then, the radius is smaller than 1. In other words, the radius is always going to be bounded between 0 and 1, right? 0 being, hey, right up here at the very top where z is equal to 4, we have a radius of 0. Once we start traversing downward on those z values, the radius keeps on extending out to try to get to that 1. Which means my radius, these drs, are changing from 0 to 1. All we need now is to calculate the heights. Well, what are the heights calculating, or what are the heights moving through? The heights in this particular case, I'm going to do this one in a different color. Let's do this one in, I don't know, let's say gold here. Alright, so now my heights. Notice my heights, even here on the boundary, are always moving, or are always calculated by z is equal to 0, so that's my lower limit of integration, up to the very top. The very top is always the cap of this figure. In other words, that cap of this figure is this green surface. So when I'm trying to calculate what are these heights for z values, they're just going to go from 0 all the way up to this surface function. But what is that surface function if z is equal to 4 minus 3x squared minus 3y squared? Well, again, we're doing this not in Cartesian, not in the rectangular coordinate system, but we're doing this within within cylindrical coordinates. So if we're using cylindrical, x squared plus y squared, that then becomes r squared. Which means my upper limit of integration is 4 minus 3r squared. And all we have to do is now integrate this particular item. This is really nice, right? Because at this point in time, all we're integrating is a constant here, and all we then have to do is integrate dz, dr, d theta, and we'll get our value. Which means I want you to keep doing the work, and I want you to get an answer. So if you need to, put pause on the video, and then we'll keep going in just a bit. Alright, make sure you do the work, put pause. Spoiler alert, it's coming up. And here it is. 5/2 pi. Oh, that doesn't look too good. I'm going to say 5 pi divided by 2. 5 pi halves. Awesome. That's a divergence theorem. And the divergence theorem, to me, has always been one of the better theorems to work with because, again, it doesn't take into account the surfaces. The surfaces are what's making up this region, and at the end of the day, we want to know what is happening to the surfaces, or what is happening to this surface as we're submerging it into this vector field. Well, at the end of the day, we don't really need to know the surfaces. All we really need to know is what is that region that is being bounded. And that's why I like the divergence theorem. So let's work with a different example. All right, so here is the next example. So for this next example, we want to use the divergence theorem to evaluate the surface integral where the given vector field in component form is yx squared for the first component. Second component is x times y squared minus 3z to the fourth. The third component is x cubed plus y squared. And S is going to be the surface of the sphere of radius 4, and this is going to be with z being less than 0 and y being less than 0. Now, this is going to be very, very important here, because when we're talking about a sphere of radius 4, we're going to be looking at the sphere, but then we're going to add these specific restrictions to it. Z values will be less than or equal to 0, meaning it's going to be below the x and y plane, and then y values are going to be less than 0, less than or equal to 0, which means it's going to be below the x and z plane as well. Alright, so let's now try to envision what is taking place here. What kind of surface we're going to be looking at if we're looking at that sphere with those given restrictions. So I'm going to go through really quickly, and I'm just going to draw my sphere, and then I'll go ahead and I'll restrict all of those values. Alright, so here's my sphere. I'm going to say this is a sphere of radius 4, and what I'm going to do here is I'm going to insert my z-axis. I'm going to insert my x-axis and my y-axis. Now, the restrictions are telling me that I must be below the x and y plane, so I need to be below the x and y plane. Alright, so I'm going to kind of keep that in mind, and actually I want to go back really quickly. And I want to move this up just a little bit more. Moved it up just a little bit more, simply so that we can say that our x-axis and y-axis are occurring here. There we are. So let's see, below the z values less than or equal to 0, that's going to mean that we're looking at all of these values down here. Alright, so that's only these values over here. And again, that's less than or equal to 0. And then we're also talking about y being less than or equal to 0. So we're only talking about this side of the sphere. Alright, we don't want positive y values, so we only want negative y values. So when we look at that, we're just looking at this wedge. Let's see if I can get this here. We're looking at this wedge on this side. There we are. And we'll cut it so that we can only analyze that wedge. So this is the wedge that we are observing when we're talking about that specific surface or that specific region. Now let's go through and let's look at this on Geogebra to see if we can extract those values. Alright, here's Geogebra. So again, this is a multivariable class that I set up, and I have the very last example here, divergence example 2. So if you click on divergence example 2, I didn't put the vector field here. I only wanted to observe the actual object that we are going to be working with. Now, in that sense, working with this object, again, we only had the bottom part of that sphere, and then we only had half of that bottom part, which means we only have a quarter of that sphere. So since we're looking at that sphere, or that wedge that we were initially observing, was that same wedge that we depicted when we were graphing it. All right, so that's really good to see that we were able to get that. And we want to make sure we get a good visualization for it, simply because, notice, your theta values typically begin at positive x value, and they traverse towards a positive y value in a counterclockwise orientation, and they typically go from 0 to 2 pi. But in this case, for this wedge, we don't have 0 to 2 pi because we don't have a whole circle being traversed. Instead, the values that are being traversed start over here in the negative x-axis, and they traverse counterclockwise to the positive x-axis, which means our theta values must go between the angle measurement of pi over to 2 pi. Phi measurements. The phi angle measurements, well, those go from the positive z-axis down to the negative z-axis using the phi values. So starting up here, they go from 0 and they start traversing, making that spherical item all the way down to pi. Well, in this particular case, we don't have that luxury that they start at the positive z-axis, but they do start at the x and y plane, meaning that's 90-degree angle from the positive z, so they start at pi halves. And they start at pi halves, and they keep on traversing downward in this direction all the way to the negative z-axis, which means my phi values will be from pi halves all the way to pi. So now that we got that understanding a little bit more, let's go back and let's go ahead and let's try to make sure we get those bounds with our picture. All right, here we are. So let's start looking at those bounds that we were talking about. Right? We want our theta values, let's switch this to orange here. We want our theta values to start from the negative x-axis, and they're going to traverse all the way till we stop at the positive x-axis. So here we are, our theta values are going to be from pi to 2 pi. Our z values, or our phi values are going to start from the positive x-axis, from the x and y plane, meaning that that's pi over 2, and they're going to extend all the way to the bottom of that z-axis, which means the theta value, or the phi values in this particular case, are going to be from pi halves over to pi. And that should capture the region that I am bounding, and this is going to be bounded with spherical coordinates. So that's really nice. So in this particular case, I want to use spherical coordinates because I'm working with a sphere. All right, so let's see if we can start doing this here. The surface integral for my vector field dot ds. That's going to be, under the divergence theorem, the triple integral over that region E for the divergence of the vector field, and that's going to be with respect to the volume that that region is covering. So in order for us to get this, let's first work on getting that divergence. So the divergence, again, we need to go through the divergence calculation. The divergence of the vector field F is going to be the dot product between del and the vector field. That should naturally give us 4xy. So again, I want you to do that calculation, taking the dot product between del and the vector field, and we should get 4xy. And this is going to be dv. Perfect. Now we need to go through and we need to use spherical coordinates. So in here, I'm going to say use, and let's not make this a star, I'm going to say use spherical coordinates. For the triple integral, or for the region E. So if we use spherical coordinates, again, we're going to change our coordinate system from the x and y coordinate system over to spherical. When that happens, we need to account for the Jacobian. All right, well, 4, that's this guy, and then x. X under spherical coordinates is rho, which in this case is going to be the radius. So radius is 4. All right, so that's going to be rho. Oh, excuse me here. So this in here is going to be rho times cosine of phi times the x coordinate is cosine phi times sine of theta. Oops, sorry. Cheese and crackers. My apologies. This is going to be rho. Rubbers. Here we go. Rho times sine of phi cosine theta. There we are. That's my x coordinate. My y coordinate is rho times sine of phi times sine of theta. Sine of theta. There we are. And then we need our Jacobian. The Jacobian in this particular case is going to be rho squared times sine of phi. Now, before I do that Jacobian, I'm actually going to move this piece here. Let's move you over here. That way we get more room. There we are. Perfect. Alright, so here we have, and then I'm going to have the Jacobian, which I said the Jacobian was going to be rho squared multiplied by sine of phi, and then this is going to be d rho d phi d theta. Alright, so again, we had our x coordinate in spherical coordinates, we had our y coordinates, we had our Jacobian. Alright, now we just need to set our bounds. Well, the bounds that we came across, well, let's go ahead and let's see. Theta was changing between pi and 2 pi. Phi was changing between pi halves and pi. And then rho is changing. What is the radii, or what is the radius that is being traversed here in order for me to calculate the whole region or that whole volume inside? Well, that radius starts at 0 and it extends all the way out to these values. That's a radius of 4. So my radius starts at 0 and it extends all the way out to 4. Now notice I didn't insert my radius in here in the actual integrand, specifically because the integrand needs to calculate for the change of all the radii. And the change of all the radii is the integral will take care of that if it's traversing from 0 to 4. If it was not traversing from 0 to 4 and we kept these as constants, it's as if we were only to be looking at the outer edge of the surface and not accounting for the region inside of it. So we have to be very careful with that. Alright, now that we have this, let's go ahead and let's simplify just a little bit more. This is going to be from pi to 2 pi. Alright, I have a constant here, it's 4, so I'm going to factor out that 4. There we are. Integral from pi halves to pi, and then integral from 0 to 4. How many rows do we have? We have 1, 2, 3, so that's going to be 4 rows. So rho to the 4th. And then we have sine phi, and sine phi again, so that's going to be sine cubed phi. And then we have sine theta and cosine theta. And this is going to be d rho, d phi, d theta. There we are. Very nice. So, once you get to this part of the integral, this is where all those integration techniques are going to come into play from Calc 2. Right? We're going to want to make sure rho to the fourth, that's not too bad of an integral. Sine theta, cosine theta, that's not going to be too bad. All that is a substitution. Or you can use a double angle by taking this 4, cutting it in half, and then putting that 2 sine theta, cosine theta here, and it'll condense into a double angle. So that's not too bad. The most difficult part will be right in here, which we'll have to integrate sine cubed phi. Sine cubed phi, we're going to need a power reduction there, and then we're going to go through those techniques. All right, or you should have gone through those techniques back in Calc 2. All right, but at this point in time, when you work through this whole technique, or when you work through this whole integration, you're going to get that the divergence theorem is going to get us that surface integral is 0. Wow, very anticlimactic, right? We spent all this time building everything, and then all of a sudden we just get that the flux across the vector field, the flux of F across the surface for this region that is being put into this vector field is just 0. All right, so I hope you all enjoyed this lesson, and I hope you all enjoyed the class overall. It's very sad that we had to end this note on a remote session, but it is what it is, and again, I hope you all enjoyed the lessons. All right.